Welcome to lecture series on advanced linear algebra. Today we are going to talk about an isomorphism in inner product space. Already we have defined what the meaning of isomorphism in vector spaces. Now isomorphism in inner product spaces is defined like this. So isomorphism in inner product spaces. See, isomorphism in vector spaces we have defined is a linear transformation from V to W, where V and W are defined over the same field, and if the linear transformation is 1 1 on 2, then we used to say that T is the isomorphism from V onto W. Now, in the case of the isomorphism in inner product spaces, we are looking not only that T will be 1 1 on 2, it has to also preserves the inner products in the spaces. So, what is the meaning of a linear transformations preserves inner product in the corresponding spaces? So, linear transformation preserves inner product. What is the meaning of this line? Let V and W be any two inner product spaces defined over the field say capital F, and both the inner product spaces are defined over the same field. Let T be a linear transformation from V into W. T is said to be a linear transformation preserves inner product in spaces provided for any alpha and beta belongs to V, inner product of T alpha and T beta must be equal to inner product of alpha and beta. See, note that the inner product of T alpha and T beta, it is an inner product in W, whereas inner product of alpha and beta is inner product in V. So, if this property holds good, then I will say that linear transformations preserves the inner products in the spaces. In the case of isomorphism in inner product spaces, I am saying that it is a linear transformation. So, let me define isomorphism in inner product spaces. A linear transformation from inner product space IPS V into IPS W, where both the vector spaces or inner product spaces are defined over the same field, is said to be an isomorphism in inner product spaces provided T is 1 1 and onto, also T preserves inner product in respective spaces. So, that is the meaning of the isomorphism in an inner product spaces. See, if I say that if T preserves inner product, then this implies that T is 1 1, implies T is 1 1. How? T preserves inner product implies that inner product of alpha alpha will be equal to inner product of T alpha for any alpha belongs to V. So, this implies norm of alpha square will be equal to norm of T alpha square. Here norm is induced by the inner product. So, this implies norm of alpha equal to norm of T alpha. So, this implies that if alpha not equal to 0, the norm of T alpha not equal to 0. This implies T is 1 1. So, it is a isomorphism in an inner product space V onto inner product W. It can be redefined like this: it is a linear transformation from V onto W which satisfies preserving of the inner products. I mean to say T preserves inner product in the spaces also. So, 1 1 no need to say, because 1 1 is coming as a consequence of the that preserving inner product implies 1 1. But it is also not wrong if I say that a 1 1 onto linear transformations between the two inner product spaces V and W will be isomorphism provided it preserves the inner product in the spaces. So, one can also redefine isomorphism in inner product spaces through some equivalent statements. So, let me talk about that one, that is I am talking about the inner product spaces when the spaces having finite dimensions. So, let me talk in terms of these theorems. It is saying like this: let V and W be two finite dimensional inner product spaces over the same field, say capital F, over the same field, say capital F. Let T be a linear transformation from V into W. Then following statement are equivalent. Following statements are equivalent. First, T preserves inner product Second, T is an isomorphism. T is an isomorphism. See, sometimes you may confuse that isomorphism we know if it is one and onto map between the two spaces, but in the case of inner product spaces I have defined isomorphism as one onto linear transformation as well as the transformation preserves the inner product. Sometimes in some book we will say that it is written like inner product spaces isomorphisms, just to differentiate between the isomorphism over the two vector spaces and isomorphism over the two inner product spaces. But here I am using simply isomorphism because I have considered this is isomorphism over the inner product spaces only. So, if T preserves in inner product, then it also implies that T is an isomorphisms. Third, T carries any orthonormal basis for V onto a orthonormal basis for W. Fourth, this is of course some sort of repetitions, but this particular case only, T carries some orthonormal basis for V onto an orthonormal basis for W. So, let us quickly prove these theorems. I want to show that if a T is a linear transformation from V into W, where V and W are finite dimensional inner product spaces defined over the same field and V and W have the same dimensions. In this case, the fourth statement, that is first statement, is that T preserves an inner product, and second is T is an isomorphism. Third, T carries any orthonormal basis for V onto an orthonormal basis for W, and the fourth one, that T carries some orthonormal basis for V onto an orthonormal basis for W. These four statements are equivalent. So, let us quickly prove that one. So, let us prove first that how one implies 2. So, given T preserves inner product, this implies that for any alpha belongs to V, norm of alpha equal to norm of T alpha. So, this implies T is 1 1. So, T, it is given to us that T preserves inner product and T is also 1 1, and since the dimension of V and W are finite and same, so it is also onto. This implies T is 1 1 and onto, since dimension of V equal to dimension of W equal to finite. So, that is why T is 1 1 onto and preserves the inner product. So, this implies T is an isomorphism. So, this implies T is an isomorphism. Now, let us prove how does 2 implies 3. 2 implies 3. Given to us that T is an isomorphisms, so it implies that it preserves also inner products. I have to show that it carries orthonormal basis for V onto an orthonormal basis for W. So, let B equal to alpha 1, alpha 2, alpha n be an orthonormal basis for V. So, T alpha 1, T alpha 2 and T alpha n will be a basis for W, because since T is 1 1. So, we know that T carries linear independent set 2 linear independent set. So, on the basis of that I can say that B is an orthonormal basis, then T alpha 1, T alpha 2, T alpha n has to be basis for W. But my claim is that this T alpha 1, T alpha 2, T alpha n is an orthonormal basis for W. Claim T alpha 1 to T alpha n is an orthonormal basis for W. We have inner product of alpha j and alpha k equal to delta j k, and we know also the delta j k equal to alpha j alpha k, which is also equal to T of alpha j and T of alpha k. So, this implies that where this delta j k is a Kronecker delta, so j equal to k, I will have this equal to 1 and otherwise 0. So, this implies that inner product of T alpha j and T alpha k equal to delta j k. So, this implies T alpha 1 to T alpha n is also an orthonormal basis for W. Now, 3 implies 4, it is very straightforward because 3 is a bigger hypothesis. It carries, I mean saying that T carries each orthonormal basis to orthonormal basis for the W. So, certainly it will also include some orthonormal basis for the V to also some orthonormal basis for the W. So, it is clear from the statement. So, now I want to show 4 implies 1. It is given T carries some orthonormal basis for V onto an orthonormal basis for W. So, now I want to show that T preserves the inner product, that is basically statement 1. Claim T preserves inner product. So, let me consider B equal to alpha 1, alpha 2, alpha n be an orthonormal basis for V. So, this is a orthonormal basis for V. So, according to given conditions, T alpha 1, T alpha 2, T alpha n will be also an orthonormal basis for W. I have to show that for any two vectors alpha and beta belongs to V, inner product of alpha beta must be equal to inner product of T alpha T beta. Let alpha belongs to V and alpha equal to sigma xi alpha I equal to 1 to n, where xi are scalar quantity belongs to the corresponding field, and beta which is equal to sigma yi and alpha I equal to 1 to n also belongs to V. So, inner product of alpha beta will be equal to inner product of sigma xi alpha I equal to 1 to n and sigma yj alpha j equal to 1 to n. So, this is equal to sigma over the I and j will have xi yj bar and inner product of alpha I alpha j, which is equal to sigma xi yj bar and delta ij. So, this is nothing, we will have simply xi and yi bar 1 to n. Now, let us see what about the inner product of T alpha T beta. So, inner product of T alpha and T beta will be inner product of T of sigma xi alpha I, T of sigma yj alpha j, and T is a linear. So, this implies that I will have this will be sigma I j xi yj bar and inner product of T of alpha I and T of alpha j. So, this is equal to again I j xi yj bar delta I j, because this T alpha I T alpha j also orthonormal. So, therefore, it will be like delta I j. So, this is equal to simply over I xi yi bar. So, this implies inner product of alpha beta equal to inner product of T alpha T beta. So, this implies 1. So, 4 implies 1. As a corollary, I can say one small results, let V and W be any two finite dimensional inner product spaces defined over the same field say capital F, then a linear transformation T from V into W will be an isomorphism if and only if dimension of V equal to dimension of W. The proof is very straightforward. You can consider as a homework also. Let me talk very quickly. See, if it is an isomorphisms, then certainly it has to be 1 1. So, this means that dimension of V has to be equal to dimension of W. Now, let me consider, so if part is very straightforward. Given T is an isomorphism. So, this implies T is 1 1. So, this implies dimension of V must be equal to dimension of W, because isomorphism 1 1 as well as on 2. So, dimension of V is equal to dimension of W, please. Now, other way, given dimension of V equal to dimension of W. So, I have to show that there exists a linear transformation from V into W which is 1 1 on 2 and preserves the inner products. Then only I can say that linear transformation is an isomorphism from V onto W. So, what I will do, consider B equal to alpha 1, alpha 2 and alpha n, an orthonormal basis for V, and also B prime equal to say beta 1, beta 2 and beta n, an orthonormal basis for W. And this is possible because both of them have same dimension and is a finite. So, using Gram-Schmidt orthonormal procedure, one can have corresponding orthonormal bases. So, now let me define. So, define a function T from V into W which is mapping alpha I goes to beta I, that is T of alpha I equal to beta I. So, if I consider like this, then I see that inner product of alpha I and alpha j. So, if I define a map from V to W which is mapping alpha I to beta I, then certainly it is a 1 1 on 2. Certainly it is 1 1 and on 2, and inner product of alpha I alpha j is equal to inner product of T alpha I and T alpha j, because alpha 1 alpha 2 orthonormals. So, therefore, inner product of alpha I and alpha j will be delta I j, and which is also equal to inner product of T alpha I and T alpha j. So, this implies T is an isomorphism from V onto W. Let me consider a couple of examples of isomorphism so that you can visualize this concept. So, let me take first very straightforward examples. It is like this: let V be a finite dimensional inner product space over the field say capital F. Consider B equal to alpha 1, alpha 2, alpha n, an orthonormal basis for V. So, I will show that for consideration of each orthonormal basis for V will introduce an isomorphisms between V onto Fn. I mean in space of all n dimensional array, and where the Fn I will consider the inner product as standard inner product on Fn. So, I have taken B equal to like this an orthonormal basis for B. Okay, fine. Let alpha and beta belongs to V, B and need two elements. So, certainly alpha will have something like sigma xi alpha I equal to 1 to n. I will be able to express alpha as a linear combination of the basis element of V. So, that is why I have x1 x2 xn which is which will give me my vector alpha. Similarly, I will also have beta is equal to something like sigma yj alpha j equal to 1 to n. So, where xi and yi belongs to. Now, if I define a function t from V into Fn, where Fn is I have taken the space of all n tuples spaces, and of course, it is also inner product, where inner product in Fn is standard inner product in Fn. So, if I define a map T from V to Fn like alpha goes to its coordinate, that is x1, x2 and xn. So, then certainly T is a linear transformation from V into Fn. Already we have checked, and you will see that it is also 1 1 and on 2. T is also 1 1 and on 2. On 2 is coming as a consequence of the finite dimensional. So, 1 1 implies on 2 also here. Here I will say that inner product of alpha beta, this is equal to, I am getting as inner product of sigma xi alpha I equal to 1 to n and sigma yj alpha j equal to 1 to n. So, this is equal to sigma I and j will have xi yj bar and inner product of alpha I alpha j. I will have like this. Okay. Since I have considered this is orthonormal, so this will be equal to I equal to 1 to n xi yj bar j equal to also 1 to n, I will have delta ij. Now, I will considering orthonormal basis this is for Fn as E1, E2, En, where our standard basis in the Fn, that E1 equal to 1 0 0 0 0, I mean Ei equal to 0 0 0 ith place 1 and it is at 0. So, in that case I have inner product of T alpha and T beta if I consider, this is equal to T alpha will be inner product of x1 to xn and y1 to yn, this coordinate. So, this will be called to sigma xi yi bar I equal to 1 to n, and this is equal to inner product of alpha beta only. So, this implies T from V into W is an isomorphism. Let me take another examples where I want to show that a linear transformations between two inner product spaces may preserve the inner products without being an isomorphisms. So, let me consider this, let V be the space of all real valued continuous function over the unit interval zero less than or equal to t less than or equal to 1. Let the inner product in V be defined by inner product of f and g equal to 0 to 1 f t g t into t square dt. So, I have defined like this inner product in this ones. Let me consider W is another inner product space is V, but inner product is given by like this inner product of f g equal to integration 0 to 1 f t g t dt. This is my inner product in W. I mean to say W is also space of all real valued continuous function defined over the unit interval 0 to 1, but equipped to the inner product which is I can say standard inner product over that space, that is integration of 0 to 1 f t g t dt. Consider a function t from V to W defined by f goes to t times f. This implies that t of f equal to t times f of t. So, this is the definitions. Then certainly t is a linear transformations, t is a linear transformation from V into W, and t is not a, so it cannot be isomorphisms. But let us see, however, if I see that inner product of f and g in V, that is equal to 0 to 1 t square f t g t dt, which is also equal to inner product of t f t g, because this is equal to over the W, this will be equal to inner product of 0 to 1, I will have t f t and t g t dt. So, this implies that t preserves inner product without being an isomorphism. So, simply preserving inner product does not imply that the corresponding linear map will be an isomorphism between two inner product spaces. That is why in my first theorems I use the word that V and W are two finite dimensional inner product spaces. So, that result is valid only if V and W are finite dimensionals. I will show you how this interesting concept introduce an interesting operator in this inner product space, which operator play a key role understanding the linear algebra. So, which we will discuss in the next class.